Knot theory. Untangling the mysteries of the Alexander polynomial and Reidemeister moves. Knot theory is a fascinating branch of topology that delves into the study of mathematical knots, essentially embeddings of a circle into three-dimensional space, math BBBR cubed. Unlike the knots we tie in ropes, mathematical knots are seamless loops with no ends, making them impossible to untie without cutting. This field is intricately linked with various mathematical disciplines and has practical applications in biology, chemistry, and physics. Two cornerstone concepts in knot theory are the Alexander polynomial and Reidemeister moves, both crucial for understanding and classifying knots. Alexander polynomial. The Alexander polynomial is a powerful tool in knot theory, serving as a knot invariant to help distinguish different knots. Introduced by J.W. Alexander in 1928, it remains a fundamental aspect of knot theory today, definition and calculation. The Alexander polynomial, denoted delta kt, is a polynomial with integer coefficients associated with a knot k. Calculating this polynomial involves several steps. 1. Construct a Seifert surface. Start with a knot diagram and construct a Seifert surface, which is an orientable surface whose boundary is the knot. 2. Form the Seifert matrix. Choose a basis for the first homology group of the Seifert surface and construct the Seifert matrix, V, based on the intersections of these basis curves. 3. Compute the Alexander polynomial. The polynomial is derived from the determinant of the matrix TV, V circumflex T, where T is an indeterminate and V circumflex T is the transpose of V. Specifically, delta kt equals sine det TV V circumflex T. The Alexander polynomial is a knot invariant, meaning it remains unchanged under isotopies of the knot, continuous deformations that do not involve cutting or passing strands through each other. Properties and applications. The Alexander polynomial has several notable properties. Symmetry. For any knot k delta kkt satisfies delta kt equals sine delta underscore k t circumflex minus 1. Evaluation at 1. For any knot delta underscore k 1 equals sine 1. Invariants. While it is a helpful tool for distinguishing different knots, it is not a complete invariant. Distinct knots can share the same Alexander polynomial. In practical terms, the Alexander polynomial is used in classifying knots. It helps differentiate knots that may look similar but are topologically distinct. Molecular biology. It aids in understanding the topological properties of DNA strands, which often form knots and links. Reidemeister moves. Reidemeister moves are essential operations in knot theory for manipulating and simplifying knot diagrams without altering the knot type. Named after Kurt Reidemeister, these moves are the foundation for proving that two knot diagrams represent the same knot. Types of Reidemeister moves. There are three types of Reidemeister moves. 1. Reidemeister move Y, twist, untwist. This move involves adding or removing a single twist in the knot diagram, which can increase or decrease the number of crossings by 1. 2. Reidemeister move 2, poke, unpoke. This move involves adding or removing two crossings by pulling a loop of the knot over or under another part of the knot. 3. Reidemeister move 3, slide. This move involves sliding a strand of the knot over or under a crossing, changing the position of the crossings but not their number. Importance of Reidemeister moves. Reidemeister moves are crucial because they provide a method for proving knot equivalence. Equivalence of knot diagrams. Two knot diagrams represent the same knot if and only if one can be transformed into the other using a finite sequence of Reidemeister moves. This concept is fundamental to the study of knot invariants and classification. Connecting Alexander polynomial and Reidemeister moves. The Alexander polynomial and Reidemeister moves are interconnected in knot theory. When calculating the Alexander polynomial, one can manipulate the knot diagram using Reidemeister moves to simplify the process. Since the Alexander polynomial is invariant under these moves, any simplified diagram resulting from them will yield the same polynomial. Examples and illustrations. To illustrate these concepts, consider the following examples. The trefoil knot. The trefoil knot is the simplest, non-trivial knot. Its Alexander polynomial can be calculated as follows. 1. Diagram and Seifert surface. Construct a Seifert surface from the trefoil knot diagram. 2. Seifert matrix. Calculate the Seifert matrix based on the intersections of curves on the Seifert surface. 3. Alexander polynomial. Compute delta kt from the determinant of TV, v circumflex t. For the trefoil knot, the Alexander polynomial is delta t equal sign t, 1 plus t circumflex minus 1. Reidemeister moves example. Consider two diagrams of the unknot, a simple loop. 1. Diagram with a twist. One diagram includes a twist. Reidemeister move 1. 2. Simplified diagram. Apply a Reidemeister move y to remove the twist, resulting in a simple loop. Both diagrams represent the same knot, the unknot, because they can be transformed into each other using a Reidemeister move. Applications in advanced topics knot theory extends beyond these basic concepts into more complex areas such as knot invariants. Besides the Alexander polynomial, other invariants like the Jones polynomial and Homfly polynomial provide deeper insights into knot properties. Quantum field theory. Knot theory intersects with quantum field theory in studying particle interactions and topological quantum computing. DNA research. Understanding how DNA knots and unknots itself during cellular processes involves applying knot theory to biological structures. Conclusion. Knot theory, with its profound connections to the Alexander polynomial and Reidemeister moves, offers a rich framework for understanding the intricate world of knots. The Alexander polynomial provides a method for distinguishing knots, while Reidemeister moves allow for the manipulation and simplification of knot diagrams. Together, these concepts form the foundation of knot theory, enabling mathematicians to classify and explore the properties of knots in both theoretical and practical contexts. As research progresses, the applications of knot theory continue to expand, revealing the beauty and complexity of this mathematical discipline.